Well, welcome back, everyone. Good morning, good afternoon, good evening, wherever you are. This is Photonics for Quantum 2. I'm Don Feiger, and I'm your host, broadcasting live from an undisclosed location in Rochester, New York, where it is 80 and sunny, as it is most days of the year. And we have a fantastic talk today. No sponsor talk and no poster talk afterwards, but we have an excellent science talk. And I want to remind you, we have talks every day at 1 p.m., except on a few days. For instance, July 3rd, we're not meeting. So I encourage you to look at the PFQ2 webpage to see our full program. Also, as you know, I'll remind you again, we have the videos and the slide sets from the speakers on the website. You have to click on the name of the speaker or the title of the talk, and the banner will expand like an accordion. And at the bottom below the abstract and bio, you can find links for the video recording and the slide set. So no further ado, from University of Waterloo, this is Hamid Majedi. Hamid, take it away.
Hello, everyone. So let me put my slides. So here I go. My name is Hamid Majedi. So I'm from University of Waterloo. Thank you very much, Don, for inviting me. So today I'm going to talk about some of the work that we have done recently on nonlinear quantum photonics in graphene silicon heterostructures. So my lab is in the Department of Electrical and Computer Engineering Integrated Quantum Optoelectronics Lab. So let me introduce some of the work that we have done and we are interested in. The major theme of the discussion today is quantum photonics. As we know, this is a very exciting merger of quantum optics, quantum technology, and nonlinear optics to tackle the technical problems in the technology of quantum photonics. So on getting quantum light sources, quantum light detectors, and in between the processing and control. So we have done work on most of these four parts. So the IQOL starts by developing the superconducting nanowire single photon detectors. And then we switch to quantum light sources. We have done some works on the nanowire quantum dots to get the single and entangled photon sources. And now we are working on some of the aspects of the waveguiding processing and control of the optical signals on a chip. And we are interested in employing photonic crystals and also two-dimensional quantum materials like graphenes. So the big picture is that hopefully we can combine these different technologies together in order to get the quantum photonic integrated circuits. So most of the time when we talk about optics, we talk about linear optics. So almost every day life involves linear optics. And the most important parameters that we should consider is the refractive index. So the refractive index, which is responsible for all reflections, refractions, and large distance propagations, are coming from the polarization of the matter when you apply electric field. So this is a known process in Maxwell's equations, when you can actually relate the D and E and the polarization vector in Maxwell's equations. But what we're interested in is that if you have intensive light, then the notion of linear refractive index is ill-defined. So when the electric field of the light interacts strongly with the material, so we have a nonlinear polarization. So that can be treated perturbatively using the equations that you see in here. We can actually go to the second order and the third order and the fourth order nonlinearity in the polarization. So the most common one, and the one that we are going to actually talk about today, and we're going to focus on that, is going to be the Kerr effect, when the refractive index of the material can be changed based on the laser radiation intensity. So obviously the N2 is very small. So this is just a typical values for it, like 10 to minus 16 to 10 to minus 11 centimeters squared per watt. So that indicates that you have to get into a large value of I in order that the second term becomes comparable with the N and not, and then you can basically change the refractive index of the material. So nonlinear optics is a very mature technology. So there are a lot of optical signal processing that one can do using these techniques like frequency mixing, self-phase modulation, self-focusing and self-defocusing, parametric amplification, EIT, electromagnetic induced transparency, and also the all optical modulation and switching. And this is the one that I'm going to focus on my talk, and I'm going to show you some of the work that we have done on the all optical modulation and switching using graphene. So having this in mind for different applications of nonlinear optics, and of course, our focus and our end goal is mostly to do the quantum optics and quantum photonics technology. So we're trying to actually hunt for large and wideband nonlinearity, electrical tunability, and of course, the ease of integration and fabrication with the conventional photonic circuitry like silicon. So most of the conventional nonlinear optics material, they do lack of the electrical tunability, and most of the time we encounter a relatively small nonlinearity and also band limited. So this is a very big goal, but we're going to see that quantum materials like graphene can provide a good basis for that. So talking about new materials, we're talking about the graphene structure. So as you know that this is the atomically thin structure of the carbons that is arranged in the honeycomb lattice. So we have electrons that they share between different sites, and you have a very strong what we call as a sigma band. This is the sp2 overlap of different locations in the crystal. And interestingly, that on the right-hand side, you see that the dispersion diagram is very different from the conventional semiconductors. This is the Dirac cone. So you see that in the low energy value regime, so there is a linear relationship between the momentum of the electrons and their energies. So then you have pi bond, which is the orthogonal to the graphene surface. This indicates that the optical properties along the different axes in basically 2D plane and perpendicular that would be a little bit different. So, but why makes graphene to be interesting for nonlinear optics? That's a very interesting physics. The main properties of the electrons in graphene that makes a large optical nonlinearity for us is the pseudo-spin and chirality, which is topologically protected, meaning that they're very stable. So if you have some deficiencies in the crystals or some trapping sites, is still pseudo-spin and chirality is intact. And that means that when you apply electromagnetic field because of the pseudo-spin, so they have inherently a large electric dipole. So if you apply electromagnetic field, so the electrons tend to get further apart, and this actually leads to a very large dielectric dipole. So when you have this, then as we know that there is a very strong and wide band light matter interaction in graphene. In fact, on the left-hand side, so you see that if you have a proper background, you can actually even see the graphene layer because of the light contrast. And this simply indicates that the light interacts very strongly with graphene. So the second picture, like in B, is taken by just a normal cell phone. And you see that completely, you see that the graphene on top of the substrate. And also some of the experiments showed that we have a strong nonlinearity. It's interesting that it can actually show positive and negative Kerr coefficient, which is interesting. So, and it's still under research to see that where we can actually employ the sign of the Kerr coefficient and how we can control that. And of course, because of the innate flexibility of the graphene, it can be integrated with the silicon optical platform. It's relatively simple to actually put graphene on top of the silicon photonics. The other thing that is very interesting, and you're going to actually see some of our experimental results, that graphene, of course, has a very fast carrier dynamics. It's ultra fast carrier dynamics, less than 200 femtosecond. And of course, the graphene is relatively transparent in terms of the nonlinear optics. So, as you know, we have that basically 2.3% of the absorption over the ideal single graphene layer. And we're going to show that we can tune the optical properties more. The most important one is the refractive index. So basically that motivates us to use graphene for classical and quantum optics technology. And you're going to see that later on, we're going to actually use graphene on top of the photonic crystal nanocavities to do the all optical modulation. So I don't want to actually go through the detail of the nonlinearity in graphene by itself. It's a very interesting and very ongoing research on the physics of the nonlinearity in graphene, but we have tackled to this problem years back, like 4 years back, and we got some nonlinear quantum optical model for graphene. So as you can see, the Kerr coefficient of the graphene, it can be as high as 10 to minus 6 centimeters squared per watt. And if you compare this with the conventional semiconductors on the right-hand side where the table is, you're going to see that that's almost 6 orders of magnitude higher. And that actually indicates that this is a very good optical, nonlinear optical materials to do nonlinear optics. So there are a lot of interesting physics. Since we don't have that much of a time, I don't go to the detail, but I draw your attention to 2 papers, one by Vermeulen's group on the left-hand side on the nonlinear optical physics, and the one that we have done in collaboration with the people in Chalmers University of Technology to address some of the interesting physics of the nonlinear optics in graphene. So let's now focus on more experimental side. So now that we know graphene has large optical nonlinearity, we started to do the measurement. Of course, we started with a very simple measurement to find out the linear refractive index of a graphene. So this is the a simple measurement that we do the transmission and reflection coefficients in order to get the linear part of the refractive index. So this is the experimental results on the right-hand side. So this is the or experiments versus the experiments that for the first time have done by Zhu. This is the real part and the imaginary part, and the one with the blue is our current work. So we noticed that because most of all the time graphene is connected to the substrate, and basically it can be n-doped or p-doped, so the refractive index is changed. But one interesting aspect is that by applying a gate voltage, you can basically tune the refractive index of the graphene. So on the right-hand side, you see a graph that it shows how the refractive in the linear part of the refractive index of graphene is changing when you apply a gate voltage, and this is a nominal values for the real refractive index, depending on the sample and the substrate, and of course that can be tuned by the gate voltage. So having done this, then we started to focus on the measurement of the nonlinearity in graphene N2. And when we started to do that, we have seen a couple of experiments giving a very wide range of numbers for the Kerr type nonlinearity, as large as 10 to minus 6 and as small as 10 to minus 12. So we decided to systematically probe the spectral and temporal dependence of the nonlinear refractive index to see the spectral dependency, and also we do the temporal dependency of the Kerr coefficient. We actually started by the Z-scan experiment. So Z-scan is a conventional technique to find out the Kerr coefficient of the material. So you see the simple experiments. So this is based on the focusing and defocusing of the Gaussian light when it passes through the sample. And it's very interesting that by doing this, depending on the focusing and defocusing on the left corner, you see that you can also find the sign of the refractive index. So it can be positive or it can be negative. So we have done these Z-scan experiments on graphene, as you see in here, and this is a normalized transmission. And if you compare this with what we have here, that we found that the positive refractive index, our first experiments was on graphene sample on quartz, and the typical N2 that we got is to 1.2 times 10 to minus 8 centimeters squared per watt. And then we have actually done the spectral dependency. So this is basically starting from the 800 nanometers to 1250. And then we use the quantum theory that we have developed in order to find out the spectral dependency of the refractive index. As you can see, it clearly shows N2 scales with lambda squared. And in the quantum modeling, we have used the relaxation times of gamma 1 and gamma 2 10 millielectron volt. That is coming from the many body particle calculation in collaboration with the Chalmers people. You're going to see that in our experiment, we actually found gamma 1 9.8 millielectron volt, very well corroborated with the theory that we have done earlier. So then in order to get into the temporal basically measurement and the characterization, we have made the pump probe experiments around our Z-scan. So this is called the PPZS. So this is a combination of the pump probe and the Z-scan measurement together in order to find out the temporal evolution. So here we go. So we have the pump signal as 102 femtosecond, and the probe is 110 femtoseconds. So we have found the relaxation of around 113 femtosecond. And as you can see, the normalized peak to peak value of the transmission through the graphene really follows the pump and probe. So that indicates that the carrier dynamics is very fast. So, this also shows that we can use graphene in order to do the optical switching, for example, or modulation, which I'm going to show you a little bit later. So this is the pump probe signal over the time, and this is our exponential feet. And as you can see that the gamma, which is h bar over tau, the relaxation time, this is from the experiments, is 9.8 millielectron volt, which is very close to the 10 millielectron volt that we have found through the many body calculation. So the detail of the results that I have presented so far, you can actually find it in this paper published in 2009 in Scientific Reports. Okay, so now that we know we have a very large nonlinear optical refractive index for graphene, and we know the temporal dynamics and we know the spectral dependence, and then we can actually go for an application, and we have chosen the all optical modulation because it was a little bit simpler based on the optical setup that we have. So in here we use a control signal, which is basically a pump. This is a laser pulse at 1064 nanometers with the duration of 120 femtoseconds. So this control basically, this is where that the refractive index of graphene is driven to its nonlinear regime. And then the signal, which is a continuous wave at 1550, basically going into the cavity, and then it's going to be populated by the control signal. So basically we have a pump that it changes the refractive index, and we have the signal that it sees the changes in the refractive index. In order to actually see that, we actually used to have a cavity in photonic crystals, and then the graphene on top can basically introduce an ensemble of the two-level system, and then we can actually have the saturation based on the graphene nonlinearity in the waveguide. So here we go. This is the image of our photonic crystals. So this is a double heterostructure. So this is a region 1, this is region 1. Region 2, it's, as you can see, there is a change in the lattice constant, and this is where you have the photonic cavity. It's a very small cavity, it's a nano cavity, and and then what we're trying to do is challenges designed for 1550. So citation units is coming from here. Setup. Setup is
See, Hamid, it sounds like your audio got scrambled a little bit. Maybe you could turn it on and off and see if it sounds better. Well, it's still scrambled. Do other people hear it as scrambled?
Yes.
Ah, okay. So you could try changing microphone if you have multiple microphones. Maybe you could cycle through a few other ones. Yeah, that sounds scrambled too. Did you want to try logging out and logging into Zoom and then come back to the slide? Okay, I think we have a short pause here because it sounded like Hamid's audio was scrambled, like it was packet loss or something. It sounded like.
Is that better?
It might be a little bit better, but it still sounds like it's scrambled there.
Start again.
Yeah, so someone, oh, that sounds better. Did you do something there?
Yes. Actually, no, I just went off.
Well, some people are recommending that you go ahead and do your audio by telephone. Is that possible?
Sure.
See, Robin, can you give him the telephone number in the chat? Or maybe someone could enter it in there. Thank you, Will.
Welcome to Zoom. Enter your meeting ID followed by pound.
Ahmed, can you hit your microphone to turn it off?
If not entered any Can I have the ID number?
There you go. It's in the chat. Now, as I understand it, someone who joins by phone will show up as a participant, and we would just need to set the person as a host. But I don't see him yet in the waiting room. Oh, here's one. Here we go.
So do you hear me now?
Yeah, but turn off your speaker because you're giving feedback.
Is that better now?
Yeah, that's good. Okay, maybe go ahead where you left off.
Okay, sure. So do you see the presentation?
Now I see an icon of a phone. If Robin has your slides, or if I have your slides, I could just show them.
Okay, just a second.
Ahmed, I think you need to share your screen again.
So it says host disabled participant screen sharing.
Robin, can you make him a host, that 1519 number? Or no, that it should just be his regular account. Yeah, can you make his regular account a host?
Done. Sorry.
Okay, great.
There we go. We can see it. Page 24.
Okay, here we go.
Looks
Okay,
good.
great. So yeah, I was explaining about the pump probe spectroscopy, pump probe Z-scan. I'm sorry. So this is the confocal cross-polarized reflectometry setup. So as you can see, we have the excitation beam. This is the 1550 nanometer is the signal. And from the other side, you see that the pump signal at 1064 nanometer, they are orthogonally polarized. So basically 1064 nanometer is focused into photonic crystals with the graphene on top. And then the excitation beam comes and basically reflect off from the cavity. And we do the cross-polarization reflectometry, and then we detect the signal. So this is the cavity spectrum at 1550 of the photonic crystals. This is basically the FTTD calculation of the mode shape. This is the copolarized IR imaging from our experimental setup. And when you do the reflectometry, so we look at the angle of the half-wave plate. So this is the angle of the half-wave plate. As you can see, it perfectly fits with the experimental data that we got. Then we start to ramp up the optical pump. So this is the 1064 from 20 milliwatt to 120 milliwatt. So as you can see, this is the red one is the amplitude modulation spectrum, and this is the thermalized cavity spectrum. So as you can see, not much is happening to the cavity when we actually have 20 milliwatt, but as we increase the power, so the refractive index is changing, and then the cavity is going to be populated. So basically the visibility is between 20 milliwatt into up to 120 milliwatt. And of course, when we have the nonlinear, interaction, also the resonance frequency is changed a little bit, but that's not really that much, as long as that you can basically populate the cavity on and off. So you can do that. So once we were doing this experiment, we noticed that every time that the pump power, we increase it, and then going into the maximum, and then we coming back. So at all of the wavelengths, as you can see in this figure, so we have some kind of a hysteresis going on. So basically, there is not one-to-one optical power that you can actually have, and that was very interesting. So that was the first time that we have seen this, and we looked for the literature. We couldn't find anything. So we repeated the experiments, and we actually have got all the time this kind of response that made us to think what's going on with this hysteresis modulation pattern. So we actually have an explanation now that because the graphene is sitting on top of the silicon, so whenever that you go from the low intensity to high intensity, there are some electrons that goes coupled into the silicon, and it's the conduction band. And when you actually lower the intensity, those electrons are released. So this is basically some kind of a trapping site. And we are now formulating that into the theory and trying to come up with the quantitative analysis of our measurement. So I think that that's basically what I wanted to talk. Of course, we actually had a plan to run these experiments. So let me come back. So run these experiments in the basically single photon regime when we have the single photon at 1550 as a signal coupled to a cavity, and then it can be controlled by a 1064 pump. So we have done some measurement, but due to the outbreak, so we were not able to finish up the experiments, but this is something that is ongoing, and hopefully when we return, so we're going to do that. We're trying to show that this can be used for a single photon regime and for single photon switching. So in summary, from the theoretical perspective, so we have developed the quantum theory of the nonlinear optical response. We actually have developed the spontaneous optical saturation. I haven't talked about it, but this is something that we have done. We have done the measurement of the Kerr coefficient for graphene, and we have done the all optical modulation and the confocal cross-polarized reflectometry of our photonic crystal nanocavities. So we have got the 100% modulation depth and basically a non-memoryless modulation pattern. So as I said, we have some works that is ongoing. So we're trying to also gate the sample on the photonic crystals in order to control the nonlinearity by electrical signal. And as I said, we're working on the single photon nonlinearity in graphene. And because that we have got into the regime of ultra-fast carrier dynamics in graphene, We're trying to see that by shortening the pulse width, so we can actually see more effect of the carrier dynamics, but our experiments somehow confirmed that all the carrier dynamics are much shorter than 200 femtoseconds. So this basically makes our optical switch extremely fast, but at the same time, we wanted to understand the carrier dynamics in graphene. So that's the team and the acknowledgement. So most of the experiment has been done by my PhD student who's graduated, Dr. Behrouz Semnani, and Sid Tahour, who's a PhD student now at Bordeaux and UW, the rest of the students down there. So I would like to thank Dr. Khoshnegar for the fabrication of the photonic crystals, Professor Safavi as a collaborator, Professor Lunis as a collaborator, and Professor Donna Strickland, who helped us a lot for the optical setup. So thank you very much. So I'm ready for questions.
Okay, Hamid, I'll clap on behalf of everyone. Thank you. And we might have to wait a minute or two for people to ask questions. I had a question here. I don't know if I'm on the right track with this, but I thought if you cool the substrate, you can keep the electrons from jumping to the conduction band. Did you try that?
Not really, but yeah, that might be something to definitely consider. It's there are a lot of processes involved in the carrier dynamics. Of course, the thermalization is quite important. But to be honest with you, it's relatively hard to tackle to that with our setup for now. And definitely we need to use shorter pulse width for that. But that might be a very good, quick strategy to basically tackle today's hysteresis problem.
Yeah, you could also, attach a copper strap to the substrate into liquid nitrogen or something, or maybe control the pulse timing so that the temperatures are modulated in a different way to see if it affects the hysteresis. At least you'll learn about the physics that that route of it. Here's another question that was sent to me. There you go, right there.
Where do you see the limitations of using graphene? So I don't know if you're talking about the limitations from the device point of view and device perspective, or from the fabrication point of view. So we can actually look at the limitations from different parts. But one thing that I can talk about is that basically most of the nonlinear optics processes really need to have a very large basically control over the refractivance, although that the natural material cannot actually give that. But once you have a graphene, and you can see that you can, by applying the voltage, for example, and changing the Fermi level, you can actually tune a little bit. Then there are a lot of potentials coming out. But the real limitations from device perspective is the integration part when we have light coming on chip. So if you notice in my experiments, everything is free space. So everything is coupled to the free space. So I think that the limitation and challenge would be that if we use graphene in an integrated platform, when when the light is coming in a waveguide mode, then most probably we're not going to get a full strength of the nonlinearity in graphene. So this is something that definitely being interesting, and we're trying to tackle to that. So I'm wondering what kind of photonic crystal cavity performance would be most ideal for modulation. Oh, that's a very good question. Actually, the reason that we have used photonic crystal, of course, it's because of the mode volume. The quality factor of the photonic crystal is very high, of course. But when you pump it with the 1064 nanometer, for example, then the quality factor comes down. So if I really want to say which one is the best for the modulation, I would go with the quality factor. So that's my answer for now. Okay, another very good questions. Are the measured nonlinearities enough to promise single photon switching? We believe so. So we are very optimistic about the nonlinearity in graphene. As I said, we have done some measurements. I can't, say for sure. We were very close. We're hoping that we can actually do it in our setup, but it's a lot of work. So, but we think that might be mostly technical problems rather than something as a physical limitation.
Okay, it looks like that's it for the questions. Thank you very much, Hamid, for an excellent talk, and thank you all for joining. And for tomorrow, I understand from our friends to the north that tomorrow is a special day in Canada. And so Amber requested to start early. So instead of 1 p.m., we're going to start at noon. And Robin, could you please confirm that for me? Is that true?
Yes, that's true.
Okay, so we're starting at noon tomorrow. Evidently, that's a better time for Amber Helmy of University of Toronto. And we're going to sign off and see you then. Thanks, everyone.
Okay. Thank you very much.
See ya.